I forgot that I had this presentation today. So this, for reason, sorry for that immediately. So in fact, the title is kind of very interesting, but I don't know how far we can go with that. Because in fact, I have immediately this kind of disclaimer there that really I don't have the answer. I want to motivate the discussion. So I want to be presenting kind of idea, and please at any moment if you want to say something, this is for me it's more a conversation, a discussion about what we are thinking about that more than okay, I have the answer and I want to tell how to do it because I don't know.
Well, the first step in the
So
conversation is always the important one. So um,
yeah.
by posing it as a problem of interpretable latent space, I think you have created a very nice uh, topic for thinking about. Yeah.
Cool. Okay, so well, the idea of this behind that I want to, or we want to understand the kind of the catchment dynamics, and from my point of view, this is kind of very correlated with the idea of the latent space, and this is what I'm going to be kind of tackling little by little. Why I think this is the key. I'm going to jump immediately to the dilemma. So this is kind of my vision of the problem, of what is the situation. So we have catchment. In some cases, in the best case, we can think that okay, we can kind of discretize the catchment very well, and that means that we can understand or we know everything in the catchment kind of in a perfect situation. If we know everything, we have a perfect distribution of the input and properties, we should have a perfect stream flow simulation. This is kind of a general idea because, from my opinion, this is what in general in hydrology we believe. And this is because we know reasonably well the dynamic of the microscale. So for the reason we have all this kind of process-based model, they are okay, you are trying to do all this kind of grid as small as possible, because in general we know kind of the main physics that is behind, I know the main processes. So for the reason we have this idea that maybe scaling up, we could kind of learn what's happening in a macro scale. But this is kind of situation at the end. We have a catchment. Really, we don't know everything. We have imperfect inputs and properties. We have imperfect stream flow simulation. So basically, and that's mean is that really we don't know, or we don't know very well what is the dynamic at macro scale. So we have a kind of good understanding at micro scale, but at macro scale is not so good. And even worse, we don't know what are the rules that allow us to move between one and the other one. At least this is my vision of the problem. So please, if you have a comment or a different about that, please let me know and we can discuss it now because this is the point of that. So if any moment you have something that just to say, just do it, please. So if we have this kind of situation, for the idea case for me is that we want to understand what's happening. So I'm representing that as kind of an engine. We have a catchment. We know that we have kind of inputs that are imperfect. We have some stream flow, and we want to understand this kind of machine or this kind of processes that are working kind of a macro scale. But really, the question is how can we learn about this engine if really we don't know exactly what are the rules, what are kind of the physics that is behind. We have just a coarse understanding about that. And if we are able to understand this kind of engine, the next question, of course, is how comparable are these engine between basic. So basically, we have the problem of that we don't know we don't know how to describe very well the engine for one catchment. And the question in the end is, okay, how we can understand many catchment in that situation. So this is kind of an open question for you. And I'm going to stop here. I want to hear your opinion about that.
Luis, when you are referring to microscale and macroscale, are microscale elemental processes in one catchment and microscale the whole catchment, or what is the
No,
physical meaning?
yeah, in the micro scale, I'm thinking that, I don't know, there are in general, if we think that we have kind of 1 meter square, I don't know if this is the best grid cell, but in general, we have a very small surface or volume, really, in general, we know what kind of the processes that are there. For sure, we don't know exactly very well, but we know that, okay, we have Richard equation, we have vegetation, we have many ideas about what is happening at this small scale. But in the moment that you are increasing that dimension of this kind of control volume, really each time the rules and the physics that is behind is kind of more fuzzy because really you don't know everything and there are kind of a lot of noise. So this kind of transition between one small scale that I don't know which one is that, but in general we know very well or represent very well, and the other is the big one, that scale of I don't know catchment, maybe a continent. There are a lot of kind of variation between one another, and really we don't know very well what's happening.
Okay.
Luis, can I ask a question?
Yes.
Those cylinders that you're showing, are they moving in tandem, or they're usually an offset, right, between the two cylinders, right?
Yeah, it should be, yeah.
Okay, just making sure. Okay.
I guess I question the premise that we know how to specify the system at the microscale. I
I
would
know,
say,
I said that in a provocative way, so please say something, yeah.
I would say that there's just as much work going on in theory trying to define or understand. We think we understand the laws of physics, and then we try to apply them at different scales. And so we even have people working at the pore scale, or and then you have to approximate things. Say, well, flow through tubes or flow through, so. So I rather think that the same problem of specification of our understanding of the dynamics is true at all scales. And we simultaneously trying to figure out how to move between scales
Yeah,
and also understand the scales. Yeah.
I agree. But my vision is that in the moment that we're working at a kind of catchment scale, for sure we know that we have this kind of constraint or kind of, we know that we have this limitation. But there are kind of, when you are going to a smaller I don't know, size, well, there are a lot of scientists that in general they believe they know more, but I agree that really there are a lot of assumptions there that really at any level of scale, really we have a coarse understanding.
I mean, a perfect example, I think, is in groundwater hydrology. They're still debating how to characterize diffusion. And Shlomo and various other people came up with models, and then other people came up and said, yes, but those models are wrong. So even just trying to implement Navier-Stokes equations is hazardous at best. So
Yeah. Sometimes I have the feeling that we feel so confident in some levels, different on some scale, but really it's not true. So it's kind of I don't know, we feel confident, but we shouldn't. We live in the level of uncertainty is higher anyway. Yeah.
I think the issues we may know most of the laws of physics in subsurface flow, but it's the characterization, the spatial heterogeneity is really a fundamental problem that we do not know how to characterize that, and that drives the system, its behavior, and like self-organizing principles. So that's where the scaling comes in. How does this behave? Like, so some of the work Shlomo was doing is characterizing some of these properties as a function of scale. What's the distribution? And then you can do moment analysis, etc., etc. So I think really the problem that we're suffering from in hydrology is a characterization issue, the heterogeneity, that we're unable to describe natural systems to the degree of variation correctly. And that's really an issue, yeah.
Yeah, I agree that it is an issue, but in in-depth or kind of a hypothetical case is if we have a perfect characterization of that, do you think that we should be able to have a full understanding of the dynamic in a catchment? Because for sure, the spatial distribution, learning or know about that is a huge problem. But in a perfect case, if we have all this information, should we be able to characterize a catchment? Or is even worse that we cannot do it in that case?
You will not get a perfect characterization, but depending if all your physics is represented, which is probably not possible. But yeah, we should get closer to the model should be better than what we have now. I think fundamental progress. I think that's why I like the issue what you bring up of scale is that if we right now lack complete theories how one scale transcends to another scale. What happens to processes? What happens? We don't have any of that essentially. How do you do upscaling with physical equations? For instance, in soil hydrology, you can measure the hydraulic functions. You can take small samples. You can measure the hydraulic functions. Now, then you can these point measurements for small samples. We still do not know how we should upscale that to get a value for a larger domain. It's a very fundamental question, and so I'm more and more attracted towards percolation theory, to be honest, describing a system which is very closely related to information theory, looking at a system in terms of critical flow paths, because there's a fundamental mismatch between what we do and the way pure physicists look at, I think flow in porous media, and that is that if you look at the Moalen van Genuchten functions and the way we describe flow and transport in a porous medium, the actual behavior of the porous medium is determined by only a few critical flow paths and not by the average behavior or like some average property of that medium. So it's a few critical flow paths. That's not in our models. So that's why percolation theory, I think, is very interesting, may help us. And maybe we can apply that to catchments. Anyway, I'm not trying to go off topic, but I'm rambling. So.
Yeah, cool. Yeah, I agree. Now, but in this sense, we have kind of two possible pathways. One is going upscaling, and the other is going downscaling. So if we are thinking in the other direction, moving in from the catchment scale, should we be able to learn this kind of relationship at catchment scale? Because for me, this is kind of more the engine that I have here. That is something we know that something is happening, that is general enough. And so how we can learn this kind of macro properties of this kind of catchment? How would we learn something like that? I think kind of, I don't know, the same happens when you have kind of the many particles in a gas and you are learning the I don't know, PD, pressure, volume. There should be some kind of relationship, a kind of macro scale that should be able to extract. But how can we do it? This is my concern at this point.
So, if you don't mind me jumping in, I was talking with Bo about this yesterday. I'd like to pose this from an information theory perspective rather than a physics perspective. The way I look at it is that if we have any particular system that we're interested in, what is information about a system? I'm going to argue that information about a system is a description. In other words, the way that we say that we know something about a system is that we can describe it. Okay. And I'm going to argue that from a practical point of view, any system that we are interested in is effectively infinite dimensional in the sense that you would need an infinite number of bits, descriptors. I'm going to go interchangeably between bits and descriptors. Descriptors could be more complex than bits, but we need an infinite number of bits to characterize everything that we think we need that's in that system, right? Effectively infinite. And we never actually do that. So what we actually do, the reason I like the term description is because we choose what aspects of that system to characterize and represent using information, bits. We never characterize everything. We only characterize the things that we think are important. And physics helps to guide what we think is important, or it helps to specify what we think is important. You mentioned the gas law, and that's an interesting one because in the gas law, you start by assuming that you have molecules bouncing around in a chamber, very idealized situation, right? And then you say that if you go up to a large enough scale, you no longer have to describe the system in terms of the momentum and position of every single individual particle. You all of a sudden you get this emergent property where you can define these descriptors called pressure, volume, and temperature. And now you essentially have reduced the Kolmogorov complexity from a very, very large number to a relatively small number. And there's this guy in France, I forget his name, but he calls it simplicity theory. He says that emergence is related to the idea that you can now have a much simpler description at that scale, right? And I would argue that that's sort of the basis of intelligence. That's how we construct models of systems. We look for descriptors which are somehow minimum length or minimum dimension, minimum length descriptors, the shortest possible descriptions we can that we can use to help solve our problem. But of course, if the problem that we need to solve is at the micro scale, then the macro scale description doesn't work. So we end up with this problem of how do we scale up, which you guys were referring to. But what I wanted to bring to this conversation is that we're thinking in terms of representing a system and we're choosing descriptors. And so even in flow through porous media, you might choose to ignore to describe the relationship between the fluid and the friction or the absorption on the surface of the particles, for example. And then somebody comes along and says, no, that's very important. And then we add, another layer of theory and so on and so forth. So the point I'm trying to make is I don't think that at whatever scale at which you're trying to model the system, I think the descriptions are always incomplete and imperfect. But we're hoping that they're complete enough that we can ignore the effects of the things that we are not describing. So if we're trying to describe the position of a cannonball or a ball which you're throwing through space, you might choose to ignore variations in wind, for example, or you might choose to ignore the fact that there are small particles being carried around by the air, which are also colliding with the ball because they're so small that their momentum has no effect and so on. Yeah. So I think we have to be careful not to get tied into the idea that we can ever have a perfect description. I think we have to understand that at every scale, what we're doing is making a choice about what things are important to describe in the context of the problem that we're trying to solve, and what aspects of description can we effectively ignore. Yeah.
Yeah. So basically, we have been talking about kind of compression. Here is a kind of get rid of the noise, but really it's noise and something else that we are kind of considering that is not relevant for the scale that we are working on. So for the reason, compression is something that should be something very important if we want to learn about this kind of engine, how it is working. The other one that I was thinking is about kind of similarity. The concept that, okay, we want to learn a representation of a catchment, but at the same time, we want that this representation should be similar to other one. And at the same time, we should be able to learn that, okay, in some cases, this representation is not going to be useful and we need to jump to another one. So basically, we need to learn about similarity, because this way we are learning generalization at the end. This is what we want. The other one is that the other concept for me is kind of parsimony. Parsimony is going to help you in the sense that, okay, we can learn a representation that is simple enough that we can interpret that and we can understand and we can kind of communicate that this representation and learn directly from that. And the last one that is kind of, maybe could be kind of controversial, but for me that we need a method to do it that should be kind of a minimal assumption. So, because we can think that when we have kind of a lumped model in hydrology, we have a minimal, it's very parsimonious, you can see what's happening. But the structure that is there is something assumption and many ideas that are behind this kind of different connection in the bucket. Basically, it's a representation that was defined by somebody. So there are many assumptions there. So if we want to learn a parsimonious representation, it should be with as minimal as possible in the number of the assumption that we're using. And in general, this is coming, well, it's very kind of correlated with the idea of using data. So the data should be telling us, okay, this is the best representation for itself. More than trying to impose a specific representation, we have to learn what is the representation that is coming in the data. So basically, with all these kind of 4 ideas, for me, what is kind of obvious is that basically the first 3 is talking about the idea of a latent space, because we have compression, we have similarity, and we have parsimony. So this is like for the reason the title at the beginning, okay, how we can learn about that, this kind of latent space. And the other one is that basically we should be using machine learning, this kind of technique that are kind of, for sure, there are kind of assumption behind, but we are trying to reduce as much as possible this kind of assumption. So we should be kind of coupling these two and learn more about this kind of latent space. Okay, so however, we have another issue here that in the moment that we want to use machine learning, we know that we have the problem of a black box. So this is kind of a paradox, because with machine learning, models can achieve remarkable predictable accuracy in hydrology, but they often, their function kind of, they work as a black boxes, and processes remain hidden from scientists. So really, we are doing very well, but we can have this kind of problem that we can predict stream flow accurately, but without understanding the underlying physics process that govern the catchment behavior. So, and this is what we want at the end. We want to learn about this kind of engine. So using machine learning, we are basically creating a bypass in the learning. And we can go directly to the input to the output, but we don't know what's happening inside. So this is some kind of the issue when we are using directly machine learning. And related with the idea of the latent space, well, why latent space matter is because it refers a kind of hidden representation learned by a machine learning model that is compressed, abstract encoding of catchment characteristic and hydrological dynamic. So basically the idea that we have that because understanding this space is crucial for model trustworthiness, physical insight, traction, transferability to engaged basin, integration with domain knowledge. So for this reason, this kind of 2 ideas for me are kind of very important. And this kind of stated the question that how can we design a machine learning architecture that learn interpretable latent representation while maintaining predictive accuracy? So how we can create this kind of architecture? And this is something that should be more than trying to be using different architectures that already are. Each day they are emerging more and more kind of architecture. We should be thinking about what is the architecture that we want, or what is the target that we want specifically, and create architecture that are aligned with our goal. So it's not just using, should be kind of creating new ideas or new representation about that.
Luis, may I
Yes,
ask you a question?
yes, sure.
I feel a little bit torn towards jumping directly from latent space to machine learning. I don't know if it's a methodological preference, or because when I think on latent space, I think of the logical representation of a system that I cannot observe completely. And so for me, it's more that I want to know what are the dynamics of the system using a latent space, because there are interactions that I cannot understand by only using observations, right? But then when I jump directly to machine learning, it's like, what am I thinking that I can solve using machine learning that it's because the latent space is gonna be represented like in the hidden layers, or because I don't know how it works, so the hidden layers are gonna take care of that, or what is your view of using directly machine learning?
Yeah, well, there are kind of two things there that, in fact, well, in the next slide, you are going to see what my idea behind that. But basically, we are working with the idea that this latent space, what is doing that latent space, or how should we work in this latent space? Because there, basically, as you said, is kind of a compressed representation that about something that we cannot measure. This is kind of, there is doing something there. But we can use this kind of latent space to help us to kind of learn, for example, the parameterization of a model. So in this sense, the latent space, the only thing is learning this kind of representation to go between, I don't know, catchment attributes to the parameters of the model. But the dynamic itself is coming from a process voiced model that is later. So depending, you can be using the latent space to kind of do a specific task, or you can keep it completely open that the latent space is doing everything. Basically, the engine and C itself is kind of the engine is doing, it's processing the input and it's doing all the behavior inside the dynamic, and then it's generating an output. So depending is about the task that we have about the latent space. And in fact, for the reason I have this kind of, I'm going to jump to this, the paper that Jan. So Jan, sorry if I try to do my best with your paper. If you have comment, please let me know. But this is kind of question. Yeah, go ahead. You are muted.
You're mute.
Before you go there, if you don't mind, I have a question.
Yeah, sure.
Sparked by your comments. I'm sort of hearing two things. One is that compression can lead to abstraction. Okay. So for example, if I take a bunch of data and I cluster the data and I have cluster centers, those cluster centers become idealized representative values for each cluster, and that's a kind of abstraction. Okay. And that achieves a kind of compression in terms of description length. You reduce the description length by identifying these typical cases, and then you can define the variations away from those typical spaces, and so you achieve a compression naturally leads to better descriptions. Yeah, that's one perspective, and that's one way of thinking about latent space. Another way of thinking about it is that you have an underlying data generating process, and what you observe is the data generated by that process. So you don't actually have access to the process itself, you only have access to the data generated by that process, right? And you could think of that data generating process as existing in some latent space because you don't have access to it. That somehow you have to take that data and you have to extract descriptors from it, which are descriptive of that underlying latent space. So that's less of a compression perspective and more of a saying maybe there's some aspect of compression, but it's like saying there's some underlying truth which I'm trying to discover, but I can't observe it, which is kind of what Lila was saying, and I'm trying to figure it out. And it may be that when I do clustering, I'm also trying to say that there is some underlying truth, and I'm going to describe it using cluster centers and descriptions and so on, but it's not entirely clear to me that they necessarily are always the same. In other words, the latent space could be the outcome of a compression process, but could also be the outcome of a, a process which assumes that there's some underlying data generating process. Anyway, I just wanted to mention that because it brought up this sort of slight
Yeah,
maybe dichotomy to me. I'm not sure. Yeah.
Yeah,
yeah,
thanks
I
for
agree.
sharing. Agree.
Yeah, and in fact, for the reason, the fourth paper, well, more three of them that I'm talking about later is about this idea that, okay, what is happening with the latent space in some way. So with the Young paper, really for me, the kind of the core innovation there is that basically you are working with a latent space that is for catchment and another latent space that is for models. So this way, basically and what is kind of interesting here is that basically you are creating clusters between catchments and clusters between models. And the kind of the multiplication of both is kind of in that case is telling you about their performance. So this is kind of the latent space kind of doing kind of both tasks. You have the task about the catchment and the other one that is kind of the dynamic. And both are working together. And the key finding from this paper for me is exactly that. Basically, you are able to create a group of the catchment in the latent space. You are kind of at the same time doing kind of model show structure specialization. So the models that are similar are kind of in one group. The same you're kind of creating cluster from models. Well, this is a good way to, or well, it's a better way to learn or kind of define a priori what should be the model that you should be using. So in this sense, now talking about the idea of the latent space, from this paper, what it's telling me that there is a latent, exists, is there, is the latent space, and in a way it has two components. We know is one component is about the catchment, kind of the property of the catchment, attribute of the catchment, and something that's related with the model. So this is kind of in that case, you have both kind of working at the same level because you are doing just a multiplication, but basically you know that there is a latent space doing something there. Coach.
So are you thinking of it as a single latent space or as two latent spaces, one with which map one to the other, or is that both the same thing?
Oh, yeah, this is kind of in this sense for me it's kind of two latent space that are working together, but at the same level.
Okay.
So, but in the moment that you have the multiplication of two latent space, you can think that this is just one, but okay, this
Sure.
is kind of yeah. But the point for me from the discussion here is that, okay, we know that this latent space exists and you have two components. Well, there are two elements that we have to consider in there. One is catchment and the other are the models. So then we jump into my paper that is about kind of real hydro-LCM. So just a small summary about that. Hydro-LCM is a modification of LCM that is kind of compressing the representation to use in general one or two cells. So this way we are getting interpretability and we are moving the loop that we have inside of the LSTM inside of the gates. So now the gates has a longer context, not just one time step. So you can have many, a sequence of context. So now the gates has more context. This is kind of the idea. So what I did in this paper is that I separated the kind of the problem in two tasks. One is the hydrolysine component that is learning the dynamic. So in this sense, this is kind of the part that later was mentioning that you have a model there that is doing the dynamic. And you have another component that is learning the regionalization. So, and in this case, really this kind of two components, they are working not at the same level, they are working one on top of the other, in the sense that this is kind of the random forest is kind of a meta model, because the model is trying to transform causal attributes and it's telling you what should be the parameters that should be using this kind of engine. So this way you are learning what is the regionalization of that engine, what is kind of the property of that, what are the weights that this kind of LSTM or hydrogen is using in this sense. So for the reason we have one model and we have the other one, basically. And well, this is kind of the key finding that I found from that is that the cell state in this sense is not doing exactly what we thought, that because it's generating a potential stream flow. So the cell state that was only one is not storing water, is trying to predict the stream flow, kind of the potential stream flow. And now the gate, because the gate has a longer context, they are kind of correcting the stream flow, but using kind of a water availability. So basically the concept of storage is in the gates, it's not in the state. This is something that was kind of interesting from this change architecture. And given that we are using random forest, we learned that we found very characteristic regions about the catchment that they have kind of similar property or similar dynamic. So in the sense about the discussion, catchment attributes, a model can be decoupled. So now before with Jan, we have this idea that this kind of, they have two latent space that they are kind of the multiplication, this is the output. In this sense, now we have this decouple that we have the dynamics is coming from one model and the other one is kind of infer or learn what is the relationship between the catchment attribute and the other one. So these kind of tasks are decoupled. One is regionalization and the other is the dynamic. Okay, then we jump to this paper that basically before we have this idea, we have is decouple the two tasks, and now we are kind of learning about only one, because what the idea here with this paper is that they are using kind of a large language model, in that case a variation autoencoder, to learn the representation to that transform catchment attributes to some kind of representation, some latent space that then can be used to infer what are the parameters that the hydrological model should be using. So in this sense, it's similar with the idea that I had with regional hydrology, and that you have a model that is transforming catchment attributes to some parameters that was used for hydrology. In that case, these parameters are used for another process-based model. But what is interesting here is that they are doing this kind of compression. This latent space is more interpretable because was trained in some way that you should be able to extract the equation. Was trained with using many thousands of equations, combination of the parameters in different relationships, using a kind of a large language model. So this way, this kind of compression of in this specific latent space is able to learn what is the equation that is behind. So this way you can extract that information. So how they did that? They use a variation autocoding. So they trained thousands of different relationships. And then they are using this kind of latent space navigation. So basically the variation autoencoder, then they use only one part and they connect it to the process-based model. And this way they can train all together. And then when this is trained, then they can use the decoder or the variation of the encoder to learn what was the relationship that it learned. So they have kind of a symbolic regression. So with that, they get more interpretability. They are doing this kind of training of the optimization of the process-based model in an efficient way. And they are getting better performance, especially in the regionalization. That is the idea, that is what is happening there. And they said that this should be more scalable because they tested different kind of scale of regionalization, and they said that the equation worked reasonably well. So in this way, they are learning this kind of scale problem in some way. So the same, this is coming for this kind of compression, this latent space that they created. In that case was just for the one of the tasks that was just a compression, because the process-based model was fixed in this sense. So this way you have these two tasks, but this paper is only about one. And what is interesting from that one, and this is kind of the relationship that they are kind of learning from that. But from the point of view of the latent space, they learn about that, okay, is the couple and the regionalization is interpretable. So this is something very useful in the sense that, remember that the task that we had at the beginning that we wanted to learn what is the relationship or what is the how this engine is working. Now we know that we can use latent spaces, and we know that we can use regionalization, and this regionalization is going to be interpretable. So this is something very interesting because little by little we are moving with this idea of the latent space, and we are able to extract different kind of part of this latent space. Then I'm going to jump to what I have been doing the last year. That is kind of have been working with the Kolmogorov-Arnold network. That is that can replace fixed activation function with learnable univariate function on edges, enable explicit representation of the input-output relationship. So this way you are kind of compressing the problem in the sense that you are not imposing a specific activation function, you are learning the activation function. And in this sense, when you are doing that, you can have a more flexible and more flexible, I don't know, a value or a sigmoid in the sense that you are more specific. And this way you are you can compress more the representation. So unlike MLP, comment? CANs provide inherent interpretability through visualizable activation functions that capture the strength and functional component. So we are able to see exactly what is the shape of the activation function or the relationship that is is happening there between the input and output. So in this paper, I created kind of two tools in the sense that one is that you can kind of correlate kind of input and output using only one input, one output. So this way you are kind of creating this pairwise relationship. So this is kind of similar to the idea of the Pearson correlation metrics when you have one-to-one. But in this sense, what I was creating here is that you can have the same idea of how strong is the relationship, but this is how strong depends on the functional form that is behind. So basically you need to know both. So in that case, with Pecan, you are learning that this is the relationship and this is the strength of that. And you can create another metrics that now you are correlating many of them. So you can jump immediately to a multivariate problem. So you have one target and you have many inputs. And at the same time, you can learn what is the relationship, the activation function that go between one another. But when we're working all together, many inputs, you are learning what is the contribution of each one and what is the shape or what is the function that is connecting one to the input with the output. So the key finding for that is that the relationship can be represented as a parsimonious representation using CAN. So this representation is smaller. And we learned that the strength of the contribution of each input depends on the function or wherever both are kind of coupled. That you cannot decouple both. And having a better quantification of the strength and understanding of the activation function or the functional form, you can facilitate discovery because you are understanding what is the relationship that is behind. And now in the context of the latent space, basically with this idea, when I have been working on that, I have the idea that, okay, we can learn parsimonious representations of the data manifold. So the data is coming with some properties in the sense that there is some relationship inside the data, but in the moment that you are trying to compress that using CAN, you can learn kind of this relationship in a parsimonious way. So you can kind of prune the information that is not very useful because you are able to compress that for a simple relationship. And the moment that you are doing that, you are able to kind of recover what is the most important relationship that is itself is in the data. So this is nice because we are able to kind of infer what is the relationship without imposing or with a minimal imposition about assumption about what should be the relationship. And this is very useful thinking the idea that we want to learn this kind of how this engine is working, because we don't want to impose any kind of constraint of that. We want to learn directly from the data. So in the next steps, what I'm thinking about the future is that, and this is kind of a question for everybody, is that my guess is that, I don't know, what do you think about how could we learn now a parsimonious interpretable, decouple, and free assumption latent space. What do you think? Because my point is that little by little we are moving with that, but I'm not sure what should be the next steps. Or I don't know, maybe you think that we are not going in the right direction. I don't know. Could be true. But I don't know what I want to hear your opinion about that.
Sorry, I missed it. What was decoupled?
Decouple in the sense that we have one part of we were thinking between input and output. We have two main tasks. One is the dynamic that is basically transforming kind of the input in output, kind of the machine. But at the same time, we have another part that is in charge of the regionalization. So each time that we're working with catchment attributes, for example, basically the catchment attribute, we are using that to define what should be the properties of the engine. So the task is kind of the couple. One is trying to learn the regionalization, and the other is trying to define what are the rules of how this engine is working. So my point is that I have the feeling that we are going in that direction, but I don't know. What do you think? Or maybe, well, let me show my vision. My hope is that in the future we should be able to get something like that. This is kind of the cartoon about that. Is that basically my guess is that we should be able to learn this kind of hydrological dynamic. We should be able to recover kind of a symbolic regression equation from that about how this engine is working, what is the relation, what is the equations. At the same time, we should be able to recover what is the regionalization. At the same time, recovering what is the symbolic regression from that. So basically, for me, this is kind of well, here I calling this idea of the latent space, but basically I'm working that this is one and this is the other one. But we should be able to record that, and we should be able to kind of learn a very simple relationship of that, or equation that is coming from that. This is my hope. I don't know, what do you think?
Do you think the catchment properties that we have are meaningful at the moment? For example, in the CAMELS US data set, if you look at the geological attributes, do they even have the ability to regionalize in general, do you think?
I don't know, from my experience there is a lot of information there, at least from the point of view of the kind of natural catchment with a few human intervention. Probably you have enough information there, at least from this kind of catchment. The moment that you are going to a more complex situation, for sure you don't have all the information. But for that, because I remember what there are some studies that they have been working with this kind of compression of the catchment attribute, and they always try to they know that they kind of compress that for I don't know 10, 12 number of attributes, no more than that, or kind of a latent space that a compression of that. So really, the information is there, but now we are using so many. Watching?
That's a really interesting question, Joe, because one way to perhaps think about it would be forget about machine learning, or rather put a human being in the place of the machine and ask the question, if I gave this human being all of this information and they had been to school and they had studied hydrology and they had some years of experience and so on, could they use that information to characterize individual catchments and to discriminate amongst them or between them? And to what extent could they do that And to what extent could they end up with um, a location by location representation, which is then capable of making reasonably accurate predictions? So
I think
part of
people
the
used to do that, right? For conceptual
yes,
model calibration, they just did it
yes,
manually through, yeah.
but part of the problem is that characterizing catchment has two parts, and one is determining the dynamical representation of the catchment in the sense of what are the dominant processes, how many state variables do we need, what connects to what, and so on, what I call the model architecture problem. And then the other part has to do with then specifying the parameters of that system once you've determined it. And it's not clear to me because an LSTM effectively does not discriminate between architecture or structure and parameters because it's all mushed into one thing. It's not clear to me that we're using the static attributes properly. In other words, the question I would like to ask somebody is, if you think that soil type, let's say sand silt clay fraction is important, then you should be able to, hopefully, from an interpretable point of view, explain to me what attribute, what kind of architecture, or what kind of parameter, or what kind of behavioral function in the catchment does that value inform us about? And we're not doing anything like that right now. We're just basically tossing it in and doing this kind of regression thing.
Yeah, it's
Uh,
funny. One of my first projects as my in my PhD, my supervisor like suspected that people were like underutilizing the geologic and soil attributes. But we actually found that those attributes are even less important than people previously thought. So yeah, it's I guess
so
it's counterintuitive hydrologically, but yeah, it seems that there's not as much information there as you'd expect.
what's his name? Ralph, sorry, Benedict, who's not here today, has been doing some analysis. He's working on a paper right now, and he found that all the soil properties, only the silt fraction seem to seem to have any relevance. And there's this paper I can show you guys later on by Ty Ferre's group, where they took the USDA soil triangle and they mapped it. Luis, you may remember this paper. And they mapped from the sand silt clay fractions using some human engineering to hydraulic properties. And when you look at that, the silt fraction essentially relates to infiltrability, how strongly infiltrable the soil is, which sort of makes sense actually if you think about it, um, because it's saying, how rapidly can water enter the ground, right? Um, and I'm sort of wondering if, as human beings, what we do is we take those properties and we transform them into some other space, some latent space, as Luis was referring to. But that latent space has meaning to us in the context of the behavioral dynamics of the problem that we're trying to study. Anyway, part of my question is, should we be just trying to map static properties to parameters, or should we be also trying to look at decoupling the problem in the way that Luis is suggesting, which is that there's one aspect which has to do with the dynamics and characterizing different dynamics of different parts of the country, and then the other part has to do with then regionalizing it. Yeah. So, Joe, say some more about what you said about your advisor, about us underutilizing the information.
Oh, I mean, it's just that was his assumption, and we set out to kind of prove that, um, the previous feature importance metrics were kind of under um, giving too little weight to these geologic attributes, but we actually found the opposite conclusion. So that's all. And there's also that other paper in from Minnesota, right, that showed that the geologic or all the catchment attributes aren't that useful. They're mostly just acting um, as like catchment IDs, and also they can be kind of basically predicted very, very well from the from the dynamic inputs.
Just out of curiosity, are you basing that claim on Nash-Sutcliffe or Nash-Sutcliffe scores? How did you decide?
Uh, which part?
Well, that the catchment attributes weren't useful.
Yes, NSE, yeah.
Okay.
In our case, we were predicting um, the hydrological signatures, but there's been other people that have been predicting stream flow directly. So yeah, it's both.
Yeah, my guess is that in some way, because using this kind of decoupling, basically, from my point of view, the catchment attribute is used to define the regions, basically. So in the moment that you are using that to define region, you are defining this to learn this kind of address, as you said. So for sure, you can use all the attributes, and basically you can find a very specific ID that you can couple or connect that. But for sure should be a minimum number, a minimum description length of the attributes that we should be using. Because basically this is related with the idea of the regionalization. So we need a minimum number to define this kind of cluster, this kind of regions. And then the moment that we found that, I don't know, I'm guessing, maybe it would be 10 attributes. The question is, okay, if we need 10, what are the 10 more kind of useful from the point of view of us, kind of, what are more meaningful? And this is kind of basically I don't know, given that kind of catchment attributes are so correlated, it's very hard to define, okay, these are the top 10. This should be and kind of get rid of all of the other ones. Because really there's so much correlation between them. This is kind of the problem for me. But should be a number, a minimum number. And this is kind of interesting for me.
Luis, can I just share the soil triangle picture?
Yeah, sure.
I guess you don't have to do anything. I just have to go here.
Yeah, this was my last slide, so don't worry. Yeah.
Okay. Can you guys see it?
Yes.
So you guys probably studied this a long time ago, but this is like the USDA soil texture triangle. So you got clay and different kinds of things, and then you got silt down here on the bottom right corner, right? Over here. And then I can't exactly describe to you their methodology, but they did some transformation and ended up with this map, which takes the soil triangle in terms of different kinds of soils and then maps it to sort of effective hydraulic conductivity, infiltration, drainage, infiltration followed by drainage, and then what is this one? I'm not sure. I'd have to read the thing, but it's sort of interesting that if you look at the silt is characterized by very high infiltration rates, high drainage rates, and moderate hydraulic conductivities. And anyway, I just thought that was an interesting. Also, you could see that the hydraulic properties don't quite match the classifications. Like if you were to redefine the classifications in terms of hydraulic properties, you would use slightly different ways of partitioning up the sand silt clay fraction stuff. So of course there's a
Yeah.
bunch of assumptions that went into this, but yeah, go ahead.
No, I was thinking that really, yeah, the seal, this kind of coordinate is interesting, but the other coordinate is interesting too, because
This
really you
one,
are where the, no, yeah, but I was thinking about the other one, the other
this
corner,
one.
that the left, yes, because
Yeah.
this is kind of defining a very specific region. Each time, okay, this kind of soils, they have a very specific behavior that is kind of different from all the other ones. This kind of
So this
coordinate is
is,
always kind of different.
so this corner is sand and this corner is silt. Yeah.
Yes.
I mean, I wouldn't have thought of anything until I saw Benedict's results, which suggested that only the silt fraction was actually informative. But, and then I said, why would silt, be an informative thing? But yeah. I mean, the other thing that's not mapped on here is you would have to actually take the conus catchments and say, how do they map onto this triangle, right? Because maybe there are no catchments in some parts of this space. And anyway, how do I stop sharing? I can never
At
figure
the
out how to
top,
stop. What?
at the top, you have a red button or something like that.
This one?
Stop sharing.
Stop
Yes.
sharing. Ah, they keep moving things around. Yeah. Anyway,
Yes. Just
Leela
one
has her hand up.
second. Yeah.
Yes, I think Hoshin made a good point when sharing that figure because he mentioned that they know that that specific variable was informative. So I guess in your work, how to connect this with information theory and to learn what it is informative.
Mm. My guess is that for in the moment that we have this kind of mapping between one another, basically we are defining that this kind of thinking in kind of neural network, this kind of connection is a very strong one. So basically the flow information is higher in this sense. Okay. Most of the flow go there and it's very useful. So this is kind of the mapping that in some way I was showing that okay, you can go with we go to catchment attribute and something, some parameter, something that is has some meaning for us. And in the moment that we are able to do this mapping is because should be kind of a flow information between the parameters and that specific the catchment attribute to this specific parameter. And this is the question, how we can find this kind of mapping without imposing that we assuming, because this is in that case this experiment that the coaching was showing us is interesting because basically it's showing us that this connection exists. So probably we use kind of just a kind of machine learning model just using seal and using the basically the hydraulic conductivity, we should be able to find a relationship. And this is kind of the idea when I was working with cats, that you are learning that this kind of connection between one another is important, and at the same time, given that it's important, you can find this kind of relationship. So this is the idea that this kind of everything is connected with the how much information is flowing there. If you have a lot of information for it, you should be able to find some relationship between both.
That makes sense. I really like the idea of separating both the dynamic engine and the regional component engine because it's kind of you are trying to um, identify what the system really needs to represent instead of letting everything go in there and be a black box and get some results, right? I think it's more parsimonious that way. And so it will be also like less computational expensive eventually. I'm not sure, but it will really depend on the quality of your data also, right? Like you're driving a high dependence on your, or is in the structure. I'm not sure. I haven't seen results, so this is a good conversation.
Yeah, I'm not sure. For me, this is my point of view because my guess is that it's kind of the optimal way to understand because you can learn the kind of the engine, what is the dynamic, because this is what we want to learn. At the same time, we have the catchment attributes that we know that we can have kind of connection, but it's kind of direct in the sense that I know they are not causal. There's kind of relationship there, so we can use that as generalization. But the other one, the other kind of the engine, really we know to have kind of very specific processes that are happening, and this is what we want to discover at the end. The parameters should be useful, but just for the implementation. So keep it there, and okay, you can use it. But really, you are learning the kind of different region where this engine that is uh, physical in the sense that you are able to understand, you have all the processes, is informative for you. But this is my opinion.
Yeah, that's a very good point. Just a final question, so to follow up on that, Luis, how do we know that the latent space is actually discovering real connections in the hydrological structure and is not compressing the information or the data for giving a better prediction? Like it's not optimizing the prediction, but it's actually discovering the structure.
Um,
Is there
yeah,
a metric to account for that, or how can you differentiate both?
yeah. For me, this is kind of a Pareto problem at the end. Is that for sure we should be able to find a very well, there is a kind of trade-off that we have to assume that okay, the moment you want to compress that and create a latent space that is as simple as possible, you should be losing some kind of performance. But the point is that we should be able to find this kind of threshold and to go to kind of a very simple to maybe good enough. Basically, we have to create this kind of Pareto frontier to define, okay, this is the closest one to the corner in some way. But
Mhm.
I'm not sure if we are in this point yet, because basically we have to be able to learn from different kind of architecture, low level of complexities, to go and find, okay, this is basically the best one. But my guess is we should be moving in that direction.
Thanks, Liz. Yeah, this is great work.
Yeah, have a comment, Luis?
Yes, please.
So I really like your analogy between catchment and engines. Yeah, I think there's something we should consider for future development for measurement because unlike engines, like catchments are changing over time. Maybe engine changes too. So it really, I think the idea of like separating a representation between dynamics and the physical like property is really important. And we can then be able to find the connection between the dynamics, like what factor affecting the dynamics. I think, yeah, it will be useful if we have some ideas that which parameters that can affect the dynamics. So in the future, we can focus on measuring those things because not unlike the engines, catchment are really larger scale and our ability to measure different things are really limited. So I think the idea is really useful because in the future we can, based on the dynamics we found, we can try to identify the parameters of the catchment we hope to measure in the future. So we can better predict catchment functions under system change.
There's another way in which the engine metaphor really helps, and that is um, it it brings to the forefront the fact that catchments do work, right? Catchments are thermodynamic, they're physical entities and they actually do work, which means, and I think Erwin Zehe and some other people in Germany are very much into this perspective, saying that you need to also use thermodynamic principles to help constrain your understanding of catchments, because it's not just structure, but the function of the catchment emerges from a structure and it's constrained by thermodynamic principles.
Is it fair to draw an analogy with LLMs, with this sort of separation of latent spaces, where you could have one system to learn the embeddings that are then fed into another system whose job is, takes those embeddings and tries to predict the next word?
Yeah, for me makes sense.
Because yeah, and then just carrying on with that, I think my response is that, obviously that can be useful, but why is it useful? Like, I think in one sense, those things may not be separable. If you could combine all of those into a single model, but it's often useful to separate them for training's sake, right? You can train one model separately from another. It's more modular. You can reuse things. Maybe from your point, maybe it makes it easier to interrogate one versus the other. Yeah. So in some contexts it may not be useful, but in others it may be.
Yeah, and for me, this idea is basically the same, because you have an embedding, and at the same time you have basically the transformer that is behind. So basically, you have to learn what is kind of the context, or where you should go and find the context for a specific task. So this is kind of the idea of the generalization there are some properties that should be defining, okay, for this specific task, you need to go to the context to, I don't know, thinking in a language, I don't know, 5 paragraphs in the past, or 5 sentences in the past. For this specific embedding, you need another one that is use just the last word. So basically, you are defining an embedding, a latent space, that is telling the other one, say, okay, this is kind of the properties that you should be using, and this way you are doing the work, basically. But for me, it's kind of the same idea. Yeah. Casper?
Jasper.
Oh yeah. Yeah, so something about the catchment attributes. I think I tend to agree with what Joe said, and that is that they have limited information. So a number of years ago, as a faculty, you have students, right? And they come to you, and sometimes they're undergraduates or graduate students, master students, and they need a project. So I had one student who really wanted to work on infiltration, soil hydrology. So at that time, someone compiled this infiltration database called the SWIC database, where people in the world put all infiltration experiments. Now, the infiltration experiments you can do in different ways, but the point is that people collect cumulative infiltration at the soil surface. They measure time and they check how much infiltration has taken place. And then some of these data sets are fairly superficial, other data sets are better. Quite a few data sets not only measured infiltration, but they also measured the saturated hydraulic conductivity of the soil. Okay, so now we're talking about that. So I spent with the students, we ended up writing 3 papers about this because first, a lot of theory about an analytic solution of Richard's equation or Richardson's equation, so that we get an infiltration function, that you don't have to solve Richard's equation. Now, you can do all that. You get a beautiful analytic solution, which is semi-implicit, so you need to iterate. So my point, what I'm trying to make is the following. When we did the inference on the infiltration, the cumulative infiltration curves, and you fit those solutions, then one of the parameters in the infiltration function is the saturated hydraulic conductivity. When I compared the saturated hydraulic conductivity with the estimates in the lab, was basically no correlation. So the ones that I infer or we infer from the cumulative infiltration curve, if we compare that with the ones that are estimated directly in the lab, there is no correlation. So then the question is, why is that? So then I investigated further, because that's more or less, I'm not saying it's a known result, but people are aware. So then what I did is those infiltration functions that we fit to the infiltration curves, they're based on assumptions. The analytic solution of Richard's equation is based on assumptions. So I derive different infiltration laws, different assumptions, and basically the point is that we will get from the infiltration curve, we will only get the measured value in the lab if the data generating process is exactly what you assume in your derivation of the infiltration function. So if infiltration indeed follows Richard's equation exactly, then if you take the cumulative infiltration curve measured, you will get the value that you'll get in the lab when you measure. And so even for a small sample, when I worked on that and we looked at structurally, my point being is, as long as our models do not represent the physics in the field very well, the parameters are essentially statistical properties. They have no clear physical meaning. That's my experience. And that's a really fundamental, I think, for them. That's why we have so many hydrological models, I think, as a next step. That's why I like your work, Luis, because I think it's really important as a next step that our parameters, if we can start showing that these hydrologic model parameters actually relate to something we can observe directly, then we're heading in the right direction, I think. Anyway, just a side note. I think that's a fundamental limitation, and it took I mean, I've done a lot of soil hydrology in the past, but it took me a while to accept this. But basically, infiltration experiments, I will go one step further. In the paper, in the third paper, we literally wrote that infiltration experiments are almost meaningless. Almost meaningless. There's very little you can do with that data in terms of informing a fatal zone flow model. First of all, you have huge spatial variability, you have crust, you have bypass flow. So what I'm trying to say is that I agree with Joe that I think there is information in the catchment attributes to inform models, but it's not that these catchment attributes will say a lot about the parameters in the models and how. Anyway, that's the only point I want to make.
That's very interesting, Jasper, because that sort of connects to my intuition, which is that they tell us more about the potential structure or architecture of the system than about its actual parameter values. In other words, yeah, because there's a relationship between structure and function, right? Function comes out of structure. And we have to first determine what we mean by structure. I want to recommend to you guys very highly this. Can you guys see my screen?
Yes.
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 Yeah, I want to recommend this book. It's called A Brief History of Intelligence by Max Bennett. And what's interesting about this book is, so you can find it on Amazon. What's interesting about this book is that he makes a relationship between neuroscience and machine learning, and he traces the evolution of organisms, and he shows how the evolution of machine learning, in some sense, parallels or reproduces some of the developments that have happened in evolution for the structure of the brain and so on. But there's a particular point that he makes which I wanted to emphasize. Oh, and I thoroughly enjoyed reading the book because I went, this is the way I would like to learn machine learning. You know, it's connected to something grounded in reality. Something we know the only example of human intelligence anyway is the one that evolution has evolved. So there's a comment somewhere in the book or in the some commentaries on the book where it says that most machine learning, that there seems to be a prevailing um, tendency within the machine learning community to say that architecture does not matter. In other words, the idea is you just take the neural network basic structure and you make it big enough and you throw enough compute at it and you give it enough data and it has enough parameters that it can learn anything. That's the idea. And what Bennett points out, as he says, is that what we learn from neuroscience is that architecture absolutely matters. Architecture representation absolutely matters. And what do I mean by that? The representation of the architecture is a particular choice about how to structure the latent space, right? Using the language that Luis is saying over here. And that gives rise to what we think of as intelligence, because it not only enables predictability, but it also enables counterfactual analysis, being able to project what might happen under circumstances that you have not seen in the data, and so on and so forth. So intelligence is not just about learning patterns from the data, but it's also about learning deeper latent space structures, which you can then use to do what if kinds of questions and analysis, which is also a kind of prediction, but it's not a prediction as to what will happen. It's a prediction as to what might happen if I were to do this, and so on, which is a much deeper kind of thing. And it's my strong feeling is that that's why we try to study physics, right? We don't try to study physics just because we want to make predictions, but we try to study physics because we want to understand how to manipulate the universe at large, not just to respond to it. You know. Oh, and there's a you can also go on YouTube and you can find book summaries of the book if you don't want to read the book. But I highly recommend reading the book. It's a great read. In fact, I'm trying to read it again now.
Contribution to make on this. So this is still current work and still needs a lot of development. I can't talk about it too much. I don't think Praveen would like me to. But I've been working on reasoning within the LLMs, and that rejoins that structural question. There is recent work that advances that LLMs can't reason just because of their structure, because deep inside they're still deep neural network. They're a matrix against which you multiply a vector to get an output, and that does not support reasoning, getting premises and building a logical process of generating hypothesis from premises. If you refer to deductive, inductive, and abductive reasoning, there are three processes that can generate hypothesis with various degrees of certainty based on the truthfulness of premises. So the statement is that without an external structure to handle that, LLMs can't reason. That recent work has advanced that recently. And talking about generating hypothesis, I wanted to take it to the group, but I think it's too early, so I'll just drop food for thought so you can all reflect on that, and maybe we can come back to it later. But I was working on another definition in the context of LLM reasoning of understanding as a byproduct of factuality verified in observations, and as a result of a formal reasoning process, such as deductive, inductive, or abductive reasoning. An example I can give is gravitational waves that were theorized by Einstein almost 100 years ago from equations, from theory. But we can argue that it was not understood because it was never observed. Well, at least not until 2015. And I use this example to illustrate the fact in this context of LLM reasoning, or more generally, machine learning reasoning, understanding requires demonstration and formalism, constructing a proof from known premises and also observation. So in the context of LLM, they can provide both, because you have the observation in the knowledge space, and you can have a side system that will build on a separate structure new premises from existing premises with a varying degree of uncertainty. And that, according to recent research or the state of the art, is not achievable with the standard stock off the shelf LLM or any deep learning model for that matter, because they do not possess the structure for that. So here's just a little food for thought that rejoins this discussion. I'm working on this, so I hope to be able to share some results as soon as I have something that is out there. I guess that's the only extent of it I can discuss.
Very interesting. Thanks, Antoine. I was going to ask Daniel to talk about this Axel Kleiden thing he put in the chat, but he's gone, so we'll have to wait for another time. I had one weird thought this week, which I wanted to run by you guys to see what you thought about it. There's this sort of discussion in the literature about the split between symbolic logic AI and artificial neural networks, or connectionist AI, right? And expert systems were early AI was sort of based on this idea that you could build up logic systems, symbolic logic, right? And then people tried to do that, and then they found that, well, yes, you can do logical, deductive, inductive, and abductive reasoning using formal logic and so on. And you didn't have to do any learning because all you had to do was specify all of the premises, the axioms, and so on, and use Boolean logic, and then you could, in principle, infer whatever it is you wanted to infer. But that sort of, it didn't exactly fall out of favor, but it got supplanted by connectionist neural networks, where you basically said, oh, well, we can't know all these things, so let's just learn it directly from the data. So here's the interesting question that came into my mind. Every neural network is built using symbolic logic, right? You have a bunch of symbols which are put together in particular ways according to particular rules. And out of that architecture that emerges using symbols, you then emerges this connectionist machine, which you can then train using, standard machine learning techniques. But it's fundamentally actually rooted in a digital symbolic representation. So I'm curious about, this goes back to the scales of how we look at things at different scales and so on. If information is fundamentally digital, right, binary, you have to start with zeros and ones, and then you can build symbolic representations using information, but then you can somehow out of that build a machine that is actually capable of learning from data. So then what's the why do we make this distinction between symbolic AI and connectionist AI? Because at some level, apparently there isn't really any distinction. And this comes up with LLMs too, right, Antoine? Because you use what are they called, tokens of the digital basis for building, and they're basically symbols. And then you put them together and you use them to learn something. So there's really not a dichotomy between symbolic AI and connectionist AI. And even the Martin Fiegel paper, in some sense, is part of that, because it's basically saying you can learn a continuous latent space which can output symbols, right? But the representation of that latent space is using symbols. So we have this interesting, complementary ways of thinking about the world. We can use symbols to somehow imagine continuous latent spaces, but the actual representation is always symbolic and discrete. So what does that say about the latent space thing that you're trying to talk about here, Luis. Yeah.
Yeah, where for sure, at some level, there is always some kind of I know what to say, but maybe a minimum number of, or a minimum representation, a basic representation, kind of the basis that we have to define. And in that case, okay, it could be bits, or could be something else, or could be symbolic. But basically, there is a minimum kind of representation or position in the sense that we want to represent the word or equation or on a network in some way. And then all the kind of separation that we are doing is kind of, I don't know, it's kind of silly in the sense that because everything is coming from the same. For me, the same what's happened when we are using this kind of idea of, okay, process-based models and database models. And okay, but I always say the same, okay, the equation that you're adding there is coming from data. So it's the same. So it doesn't exist this idea, okay, we have database model, process-based model, because everything is coming from the data originally. So there is kind of idea that basically we are creating this separation that is kind of arbitrary, or we would like to create this kind of separation, but really at the end everything is coming from the same. It's coming from the data, and the data is coming from a specific representation that we created about that. So I don't know, my guess is basically is some human definition or arbitrary definition about that, but really doesn't exist.
Go ahead, Leela. You don't have to wait.
Hoshin, I'm not very familiar, but is the difference between symbolic AI and neural networks really fundamental, or is just about how learning happens in each of them?
Well, my understanding of symbolic AI is that you use symbols to represent objects or relationships or whatever in the world, right? So you choose what you want to represent, and then you assign symbols to them. And then you use Boolean logic, if-then statements, and so on, and or not, all these kind of things, to characterize things that are true and not true, right? False. This is sort of the formulation. So if it's raining outside, then there's a high chance that the road is going to be wet, right? You can make up statements like that. And in the early days, they said, well, that's knowledge. That's right. So let's create medical databases in which we put all of this stuff in, and then you can query them. And a computer-based medical database can essentially store and contain a lot more information than an individual could. And so you could build these very intelligent systems which would use inferential logic to be able to arrive at conclusions. So you would ask the patient a question, is this true? Is this true? Is this true? Whatever, they put it in. And then you'd say, well, probably you have a problem with your liver, something like that, right? I mean, that's not different from diagnostic analysis, right? You go to a doctor and they ask you a bunch of questions, or you go to a Chinese medical specialist and they will take your pulses and they will look at the color of your eyes and so on, right? These are all symptoms, and then from those symptoms, they will diagnose the underlying cause of the disease or hypothesize about it, right? Something like that. So that's my understanding of what they mean when they say symbolic AI, right? But I'm also trying to think of this more from an information theory point of view, right? So if, for example, I give you a table of numbers of values of X and Y that I've observed, right? each of those values of x and y requires a certain number of bits to store. They're essentially discrete or digital, although, right? So the observations themselves are all discrete, right? And then if I put those values and I look for patterns in those values, I see that they kind of fit this kind of pattern. And so now I can compress this table of numbers, x and y, right? It's really a compression. I'm trying to reduce the description length of my data. And I can now say, I can write this as y is equal to mx plus c, plus some so I've extracted a pattern from it, right? And what I find interesting about this is if you ignore the EJ part, right, which is just the errors, which you would have to describe, if you throw that part away, right? So that would be the part that you can't describe using an algorithm anymore. That would be, you can only describe probabilistically, the Shannon part of it. Then essentially what you've done is you've taken this whole list of tables and you've compressed it by now replacing it with 1, 2, 3, 4, 5, 6 symbols, right? So it's still a symbolic representation. The original one was symbolic in terms of numbers, but now it's symbolic in terms of these and so these things are the latent variables, right? The form of this equation, y is equal to mx plus c, is a latent, it's a descriptor. And then the values of m and c are descriptors. And now I've done a major compression because I need far fewer bits to store that information over there. Okay, but something very interesting just happened because now I'm implying that y and x are related, that there's some continuous space of values of x and values of y, and there's a continuous relationship between them. And that's entirely imaginary, right? It's not in the data. It's something I've imposed on the data. So I'm thinking of this as my latent space representation of the data, right? I'm saying there's a data generating process and it has this structure. So I've just invented continuity. Okay. And there's an article of fate there because it says that if I vary x by a very small amount, y will vary by a very small amount. But that's something I am adding as information. It's not there actually in the original data. Anyway, this is.
Yeah, but
Go ahead.
no, I was thinking is that, but in if we were representing that as just a table, basically you have every data point that you have there, or you have this kind of symbolic equation. Basically, the main difference is that is what the basis, the basis function that you are using to represent that.
Yes.
That in one you are using one it's very simple. That okay, basically you are using kind of a delta Dirac that is a point to represent only one, and the other you are using a kind of a linear one. But you are using this is kind of arbitrary. Basically, this is the part I was saying that basically we are defining different representation. That some of them are very simple, and others are kind of longer in the sequence length. So basically, we are defining this kind of depending on the problem that we have, because in some cases one representation is better than the other one. But at the end, everything is coming from a representation that we define it as user.
So you're using the word basis function. I was using the word pattern. They're more or less the same thing, right? In some sense, like a fundamental pattern, right? Which we then impose on the data, and then we see how well the data sticks to that pattern.
Yeah, because in the same example, you can have a parabolic relationship. And then if you want to represent that with a linear one, you need to have many pieces to represent a parabolic one. But if you have a representation that you already have a parabolic function, you will need a very short description.
Yeah.
But depending on the description, and some way you're defining this kind of dictionary, but at the end it's coming just this data. It's, okay, you are defining how you're representing that data, and that is affecting you what you are going to find. What is kind of the parsimonious representation that you can find with that.
But I guess what I'm saying is that the world is the world through the data may imply a pattern, but the pattern came from me, not from the world, right? I somehow had to add something to the data, otherwise I could not extract the information from it.
Yeah, sure.
Yeah. And our choice of what basis function, so that goes back to the earlier point with Antoine, but the architecture absolutely matters. The choice of structure we put on it determines what kind of information we can extract and what kind of analysis we can do with it.
So at the end, we are choosing how to do that continuous representation. And we assume that that is the actual process structure. And we can go as complex as we want, but then we start losing interpretability, right? Because we say, for instance, if we make the structure, the representation more complete, and we go from nonlinear from a linear representation to a nonlinear representation, but then we start losing the way how we can explain the relationship between those two variables, because now we have many variables, and so we are kind of gaining. Oh, go ahead.
No, I think interpretability comes about because we build a dictionary.
Oh,
right?
you're right. Yeah. That's not the right word. It's not interpretability, but yeah, you're right.
But
You're right.
in some way, what you were saying, that the moment you are increased complexity, you are losing interpretability. But
Right.
I'm not sure really, because depend on what is level of complexity. Because in the same example, if you have linear, the only thing that you know is about linear relationship, and then in some moment somebody said, okay, look, you can learn about parabolic equation, and then you can represent everything as parabolic. And in some cases, okay, you're learning very fast, or the representation is very simple.
But
But
everything
if
is
you know
parabolic.
what this means, really this additional complexity is not a problem. It's in the moment that you know, and you added this kind of parabolic relationship into your dictionary.
Right.
So really more
You're
complexity
right.
doesn't mean that you are losing interpretability. Really you are increasing your dictionary.
So
Or
it's
you need
almost like
some kind of
this reminds me of a statement by you guys know there's a guy by the name of John Castee who is or was at the Santa Fe Institute, and he wrote a book called Complexity, Science of Complexity, or something like that. And in I think chapter one of his paper, I can't remember which, there was a little blurb at the beginning where he says, "I've never seen a system, no matter how complex, which when viewed from another point of view did not appear even more complicated." And what I liked about that was he's basically pointing to the fact that we choose a particular structure. So we can add stuff and we can make it less interpretable by the way we add it, right? And we can choose a particular way of doing it, which has to be very consistent with the language that we have chosen, which results in it, instead of appearing more complicated, it appears more simple because we build that dictionary and that knowledge in a particular way, right? So the moment you've learned a sign function, you know what a sign function is, and you understand it, you don't have to build it up from rectified linear units anymore. Yeah.
Right.
And somehow mathematics seems to be the science of how to build that language, right? The,
Mhm.
there's something uh, if you look at the set of functions that we have learned when we went to school and that we use to construct our equations, our symbolic equations, they're a limited set of operations that we perform, um, which for the most part seem to do the job, right? If you look at the equations, there's limits, use sines and cosines and tans and hyperbolics and
Mhm.
logarithms and multiplication and division and addition and so on. But it's not an infinite set. It's a finite set. Yeah. And then at some point we put them together and we say uh, hydro-LSTM. And when I say hydro-LSTM, I now understand, right? I only have to use one symbol to represent everything that's buried inside that, right? Roy, you've been very quiet.
Yeah, I'm preparing for my classes at the same time, and I'm just listening to the
Okay,
discussions. Really, really good conversations. Yeah, yeah.
you're multitasking. All right.
Yeah.
All right, guys, I think I've got a seminar coming up in 8 or 10 minutes, another meeting. That was really wonderful. Thanks, Luis.
Yeah.
Much appreciated. I think,
I did my best to to help in the discussion.
well, well, it was important because this concept of latent spaces has been coming up more and more. And it's very, very clear that it's something very fundamental to the learning process, it's something very fundamental to information theory, very fundamental to machine learning. And the more we come at it from different perspectives, I think we're gaining some. Uh, we're trying to understand what that actually means, right?
Means, yeah, exactly.
Yeah, because in the beginning you hear the term latent space and you think you know what it means, but apparently it's a much richer concept than you might just get by just picking up a machine learning textbook or something like that. So I think it's going to take a lot more discussion and
Yeah.
Yeah.
Yeah, but I gave just a little flavor about that.
sure. All right, guys.
Luis, I just have one question. Do you want me to share our discussion today in the YouTube channel right away,
Yeah,
or do you want to wait? Okay,
no, it's okay.
cool.
Yeah.
And yeah, for our next session, we don't have a presenter yet. So if any of you wants to volunteer, you're very welcome to present next time.
I'll try to remember if I forget, Leela, I will send, there's a deep dive books YouTube compression of that book, Brief History of Intelligence, which I will send you guys the link to. Sometimes, you can listen to it while you're driving to work or whatever, because they're
Yes,
relatively
I
short.
already downloaded the audiobook. That would
And
be a good idea.
somebody else was going to say something, but I just wanted to say the other thing that's been intriguing me recently, Yang, you're here, is that one of the main points that the book focuses on is the development of reinforcement learning as a learning strategy and its various stages. And one question we might discuss in some future meeting is why is it that we don't use reinforcement learning as a major paradigm for building models in the earth sciences? Because it seems to be a very powerful and interesting concept, particularly when you're dealing with uncertain environments and environments that might actually change, right? As somebody, Yang, I think you mentioned earlier. I know, Yang, you mentioned reinforcement learning to me a long time ago, and it's been taken a long time to come back to it, but I'm starting to get more and more intrigued for example, I assume that future LLMs will be based in reinforcement learning, but also that system models should presumably be based in it. Yeah.
Yeah.
Reinforcement learning is heavily used to tune base foundational LLMs for human preferences. This is the second step of learning in LLM. I'm pretty sure it's used in every model as the secondary step after training the base knowledge model.
Mhm. Yeah.
So you're saying once you have a sort of a foundational thing, then you can apply it on top of that. Is that, yeah.
And there is super interesting research about other methods to apply a reinforcement learning method with reduced complexity and increased performance. One I can think of is called DPO, direct preference optimization, and they convert the base functioning of reinforcement learning into loss functions and other optimization directives, so you can train for those behaviors with a more direct approach that does not necessitate too much relearning. There's a lot of very interesting paper on this subject. I can share some with you, with the group.
That's
Okay.
great. Yeah.
Leela, if we could find somebody who might give us a little primer on reinforcement learning, that would be maybe very helpful.
Okay, yeah, I'm gonna share with the team, and yeah, I don't know, Antoine, if this is something that interesting you. If you want to take the lead, you can tell me later, or Jan, or yeah, I know everyone has a very tight schedule, so yeah, just an invitation, but don't feel pressure.
Anyway, it was nice seeing everybody.
Thank you so much.
Thank you.
And Luis.
For the discussion.
Thanks,
Thank you,
Luis.
Luis.
Bye-bye.
Bye-bye.
See you
Bye.
next time. Thanks.